Hello, I'm Bettin, and this is my presentation, Assessing Minnesota's Wind Power Potential. To start out, we'll be just showing you an outline of where the presentation will go. To start out, we'll have the most basic questions and assumptions. To start out with the project as to what the general goals and ideas that motivated the project were. Beyond that, I will explain why you should care about the wind landscape in the state of Minnesota, as well as why I chose to focus on wind power for this project before finally going into the final maps and models for not only the wind landscape, but also an assessment of agriculture and agriculturally developed lands on the wind's landscape until finally going into my conclusions. Some of you may be aware wind power has significant energy potential, but like all power sources, whether that be nuclear, biodiesel, or oil, it requires significant amounts of land to be developed in order for it to provide that energy. And like some other forms of energy generation, certain areas are better for the creation of wind farms and the construction of wind turbines than others may be. The question is, how do we assess what areas are better for expansion? Whether that be what sorts of requirements that areas for expansion would need, what would make areas be less ideal for the expansion and construction of wind farms. But beyond just what areas are appropriate for expansion, we need to know how much would be needed. In this case, for this presentation, I will be showing how much land would be needed to be developed to cover all of the state of Minnesota's power needs. And the further question is whether or not agriculture can have a significant impact on the assessment of the wind landscape. The question, some may be asking why they should care about the expansion of wind power and other green resources, and in this presentation I will be focusing on two main areas as to why this is an important topic for discussion and further research, and those two areas are fossil fuels as well as energy sprawl. One significant factor in relation to fossil fuels, whether they be oil, natural gas, or coal, is the high carbon impact that these energy sources have. Over the years, these energy sources have contributed significant amounts of carbon, which in turn contributes to global climate change. Though there are methods to prevent large amounts of carbon from escaping into the atmosphere, research into these methods of carbon capture indicates that they are too expensive to be feasible. Further, these methods would require even greater amounts of fuel, as well as would require significant amounts of land in order to store the carbon not released into the atmosphere. The more these methods were used to offset the carbon impact of energy generation, the greater cost of fuel usage as well as land usage for storage, making the practice not viable for large-scale use. Further, some societal movement away from fossil fuels has already begun in the case of certain energy sources, as indicated by the graph shown. However, there is one notable exception to this. The graphics on the previous slide show a decrease in the use of certain types of fossil fuels, namely oil and natural gas. Other types of fossil fuels, such as coal, have actually increased in usage, which has led to an even greater amount of carbon to be released into the atmosphere. If efforts are to be made to combat global warming, much more significant investment into green technologies in order to offset this increased coal usage will need to be made, meaning that assessments such as the one in this project are even more and more important going forward. Beyond fossil fuels, the other major factor that this project seeks to examine is energy sprawl. Energy sprawl refers to land usage in relation to power generation. With different types of power sources, different amounts of land are required for their usage. The amount of land needed to produce a gigawatt of electricity from nuclear power is significantly different from the amount of land needed to produce a gigawatt of energy from biodiesel or solar power. Oftentimes, when assessing different methods of energy production, a choice needs to be made, whether greater emphasis will be placed on energy efficiency or on the potential environmental impact of that power source. Certain potential energy resources, though they may have a more negative environmental impact, oftentimes are much more efficient when it comes to land usage, such as with coal or natural gas. Meanwhile, other potential energy production techniques such as biodiesel or ethanol, require much greater amounts of land use, though do not have the same sorts of negative environmental impacts. Furthermore, not all energy production methods may be viable in certain areas, though they may be more efficient and have less of an environmental impact. They may not be feasible in a specific geographic area. Regardless of what method is chosen, there will be a significant need for more land to be used for the production of energy, with one study predicting that by 2030 we will need 260,000 square kilometers more for the production of energy. In the case of many renewable technologies, such as with wind power and solar power, there is an intermediate value. What this means is that while they may not produce as much power as quote-unquote less environmentally friendly methods such as coal, they do not require the same large amounts of land use such as biodiesel, making them a viable potential alternative. One intermediate power source I chose to focus on for this project was wind power. The question is, why focus on wind? This isn't due to two major factors: negatives in relation to other green energy sources that I saw as important, and potential benefits of using wind power. Such negatives for other power sources include the high cost in certain cases, such as with solar panels, as well as the much greater land use requirements of certain types of biofuels. Further, other types of green energy, such as nuclear power, have significant political hurdles that wind power simply does not have to overcome. Potential benefits of wind power includes large amounts of open space after the construction of wind turbines, as the graphic on the right clearly shows, which could lend itself to potential development for other power sources, whether that be biodiesel or solar, or could be used for farming. Further, unlike other types of green energy, wind turbines do in fact work in cloudy and rainy conditions, and in fact can be more efficient in the rain. Some of the background research into wind power that I did included not only assessments into the total land use requirements of wind farms, but also into general background on the energy potential of wind power, as well as the potential societal costs that its usage had. David McKay's Sustainable Energy Without the Hot Air was a great resource for this process. Now, this brings me to my actual research question for the assessment done for this project. What areas are most sustainable for wind power development? Now, this assessment focused entirely on the state of Minnesota, and then later parts of the assessment focused on the southwestern area of the state, specifically around the Buffalo Ridge area, the reasons for which I will get into more later in the presentation. To begin, we need to assess what areas of the state are most profitable or most viable for the expansion of wind power infrastructure. This was assessed through three main areas: energy demand, existing energy infrastructure, as well as high wind speeds. By using a layer that represented lights visible at night, I was able to show areas with high energy demand, and using locations of electric substations, I was able to show existing energy infrastructure. Further, I was able to use a layer that showed high wind speeds and bring all of those into a raster calculator to create a layer showing profitability, which we can see here. Darker areas representing areas that are more profitable in relation to wind expansion, lighter areas being less profitable. Beyond showing which areas in the state were best for the expansion of wind power, we need to show which areas are not viable for the construction of wind farms. Obviously, you cannot have a wind turbine in a downtown metropolitan area or within a certain radius of airport. Further, there are areas of the state in which wind speeds are so low that having a wind turbine would simply not be cost effective. Using those three categories, as well as lakes, since it would not be viable to put large-scale wind farms inside of lakes, we were able to create a map showing showing these excluded areas, which can be shown here. The gray areas being excluded, the light gray areas being excluded, dark gray areas still being viable. Now, by combining these two models into one single model, we are able to create a map of the wind landscape of Minnesota. Shown here, we can see areas in green, which are more profitable for the expansion of wind energy, and areas in red, which are less profitable, with white areas showing excluded areas. As the previous slide showed, the area of the state that was most viable for the expansion of wind power is the southwestern region of the state, specifically in the Buffalo Ridge area. Using a fishnet, I was able to show which areas of this most profitable area were the most profitable, with darker green areas being more suitable for wind energy expansion. Now that we know which areas of the state are most viable for wind power generation, we need to know how much land is needed to cover the state's power requirements. We know that the state requires 4,786 gigawatt hours of electricity per year. If we assume that wind farms generate 1.5 megawatts of electricity per square kilometer, we can determine the total land usage needs of the state, which in turn comes to 346.3 square kilometers, or a roughly 19 by 19 kilometer area. The red square on the lower left of the left-hand graphic shows what that 19 by 19 square would look like. However, since the purpose of this project was to determine which areas were most viable for wind power generation, using the profitability of that area, as I've already shown, I was able to create a blue graphic which contains the same geographic area in areas more suited for wind power expansion. Now that we have shown what the land use requirements for the state of Minnesota to be powered on wind power actually are, we need to consider another factor which may impact which areas of the state are most viable for wind energy production, namely agriculture. Due to the land use requirements of wind power leaving significant amounts of open space between turbines, it may be a viable option to put emphasis on expanding into areas of agricultural development, since these lands have already been cleared and developed to a degree. This area, which shows corn production in the state of Minnesota, is a good baseline to figure out what effect agriculture may have on the models I've already shown. Here's the new profitability model, which includes this new agricultural layer. As you can see here, once agriculture was factored into the profitability model, there was some change to the map, though that change is difficult to make out, and it did not significantly alter the profitability landscape, in that the most profitable area continued to be the southwestern area of the state. Here you can see that agricultural layer was added into the overall wind landscape model. In turn, the wind landscape, as with the profitability, has changed somewhat, though that change is more difficult to make out. Once again, the most profitable area in the state continues to be the southwest area. In conclusion, the wind landscape shows that southwestern Minnesota is the best area for wind development. Furthermore, we were able to show that 361 square kilometers is the total area of wind farms that would be required to power the state of Minnesota. And finally, when factored into the models, agriculture does not significantly impact the assessment. Though it may change the wind landscape somewhat and affect profitability, it does not impact the overall assessment. Future research into this topic could include assessments of the total cost of these wind farms, as well as what potential environmental impact they may have, as well as what potential there could be for further energy generation by including solar power and biofuels into that area, as well as applying the same lessons learned here to other states, and then reassessing this wind landscape further in the future when greater wind power is needed. Thank you all for viewing this presentation. Have a splendid day.